Well, the question's always asked is, why do we use lime? Why don't we use the sort of more modernly invented materials? But there are really three very good reasons for using it. And the first of these is that it has been used traditionally and it stood the test of time. The Pantheon in Rome has a dome, the diameter of which is 142 feet, I think, and it's completely plastered in lime and is as good as new. It's a beautiful structure. And so tradition and standing the test of time is certainly the first reason. The second reason is its breathability. And that means a huge amount on an old building. What you find is, if you use cement pointing, is it's rather like a rather bad raincoat, in that cement pointing and rendering won't let a lot of moisture in, but once it does get in, it'll never get out. And so what you get is the effect, the freeze-thaw cycle as it's known, and you get the water behind the cement pointing freezing in the winter and blowing the cement pointing off, complete with bits of stone and debris. And you can see ruinous work that's been done with cement mortar, and even worse with cement render. And the third reason is its flexibility. And lime mortars do flex, and you can see this in old buildings that have got lots of bulges and lumps and bumps in them, but they're still standing and they're still fantastic structures. And so they will take a lot of movement, even earthquake movement and that type of movement, and settlement, and every other sort of earth movement you can think of. And they also have a self-healing quality, but it's probably easier to explain the self-healing when I just explain the lime cycle to you. I should point out at the beginning of this that the lime cycle, which I'll just demonstrate to you now, is actually creating non-hydraulic lime, what we know as fat lime. But of course there are hydraulic limes which have different strengths, and they all have different uses and different purposes, but all equally valid. Now, if I demonstrate this to you, here we have the freshly quarried limestone, and this is actual local limestone from very close to here. And this is then burnt in a kiln at between 800 and 900 degrees centigrade, and maintained at that temperature for about 8 hours in a traditional kiln. And then when it cools, one has gone from something called calcium carbonate, which is limestone, to calcium oxide, which is the quicklime that we see here. And the calcium oxide is a much lighter material. It's lost about 40% of its weight. These pieces are very small, but you can obviously burn much bigger lumps and create much larger lumps of quicklime. Now, when this quicklime, as it's known, this calcium oxide, is added to water, and if I just add a little bit to it, and this is perfectly cold water there, you will see actually that there's an exothermic reaction which is creating a great deal of heat. And this actually creates lime putty. And lime putty is what we then have to create lime mortar. The lime putty that we've now created in this tub creates a wonderfully creamy putty. And when this is mixed with aggregate and is allowed to carbonate, which means that water is given off and carbon dioxide is absorbed, then it reverts virtually to calcium carbonate, but it actually creates a lime mortar which will set and carbonate and create a mortar that's good enough to build buildings with. And we see in the next tub some of the lime mortar that we've created, and the block beyond here is a piece of lime mortar that we've made. And that will set and is a breathable material. It is an excellent material for building and repointing with, and it is the one and only material one should use when restoring old buildings in this fashion. Over here we have a tray of lime mortars which are made with different sands and different proportions of lime to get different textures, different colours, different strengths. And we have many trays of these so that they can be matched to the existing lime mortars that we find in buildings. Hydrated lime is actually something quite different. Hydrated lime is quicklime that has had just the right amount of water added to it to turn it to a powder and no more. However, if you do this with ordinary quicklime, then you actually create a powder that is still quite reactive. And so normally you add sufficient water to create a lime putty, and this can then be kept underwater, away from carbon dioxide, for many months or years before it's used. However, hydraulic limes come in a hydrated form, which means they have had sufficient water added to them to allow them to turn to a powder, but no further. And this, as long as they are kept in airtight bags, will last for many months. Hydraulic lime is made from a limestone that contains much more aluminas and silicas, and this, when burnt, creates a much stronger lime, a lime that will have a real hard set to it, and the more eminently hydraulic a lime is, the harder that set is. This has certain disadvantages, but the advantage is really when you're using it in exposed conditions. For example, on wall cappings, coping stones, buttresses, chimney caps, and even on, for example, harbour walls in very extreme conditions. You're creating a lime mortar that will really stand up to very severe weather conditions. But the important thing to do is to use the right lime in the right situation. Here at St Bartholomew's Church, Richard's Castle, we have the perfect example of where we've used an eminently hydraulic lime to rebuild the brick trough that runs around the base of the church, which is susceptible to frost and wet. And as we climb the wall through the plinth, we've used a moderately hydraulic lime in order to counteract the weather that will receive. As we then climb through the wall face, where the stone is very soft and friable, we've used a fat lime in order to provide a weak mortar that won't be destructive to the stonework. On the buttresses and the copings above, again, we've used a hydraulic lime when repointing, as these have to take the batterings of the weather.